This problem asks us to solve the system of equations using the addition method. So to use the addition method, I want to look at my equations, and my goal is to add the equations and eliminate one of the variables, have one of the variables drop out. I can see if I added the equations right now, nothing would drop out. So my next idea is, could I multiply one of these equations by a constant that after I multiplied it by that constant, then a variable would drop out. So is there anything I can multiply 2 by to get 3 or 3 by to get 2? No whole number. I'd have to do a fraction. I check the y's. Anything I can multiply 5 by to get 7 or 7 by to get 5? No. So since that didn't work, my next step would be, okay, well, I'll have to multiply both equations and change both of the equations in order to get something to drop out. I'm going to look at the x terms because I notice they already have different signs, and that's one thing I want. So I'm looking for a number that's a multiple of both 2 and 3, a number that they both can arrive at if I multiply them by constants. And so the smallest multiple of 2 and 3 would be 6. So if I multiply the top equation by 2, I'd get a positive 6x. And if I multiply the bottom equation by 3, I'd get a negative 6x. And then I'd be able to add and have a variable drop out. So that's what I'll do. I'm going to multiply this top equation, the whole equation, by 2, and the bottom equation by 3. And remember, when I do that, I'm really multiplying each term on each side of the equation by the 2, and then each term on each side of the equation by the 3. So I'll rewrite my system of equivalent equations. I have 2 times 3x, I have 6x, plus 2 times 5y is 10y, equals 2 times negative 6, which is negative 12. And be really careful that the constant you're multiplying by multiplies each term on both sides. For the second equation, I'm multiplying everything by 3, so I have 3 times negative 2 is negative 6x, plus 3 times 7 is 21y, equals 3 times 4, or 12. Now I have a system of equations where if I add them up, I'll get one term, the x's, dropping out. One of the variables will drop out. 6x plus negative 6x is 0, and 10y plus 21y is 31y. Negative 12 plus 12 is 0. So I have 31 times y equals 0. So to solve for y, I'm dividing both sides by 31, which just gives me y equals 0. So for my solution, I have part of the solution. I know my y value is 0. Now I still need to know what the x value is. The way I find that is I go back to my original equations and I choose one of them, and I'm going to substitute 0 in for y and find out what the corresponding x will be. So I'm going to take the equation 3x plus 5y equals negative 6, and in for y I'm putting 0. So I have 3x plus 5, and then I'll put in the 0 for y. 5 times 0 equals negative 6. 5 times 0 is just 0, so I have 3x equals negative 6. Oops, excuse me, divide both sides by 3. X equals negative 2. So that value, negative 2, gives me the x coordinate. So here's my point that I'm saying is a solution to the system, which means if I graph the equation, I'm expecting those two lines to intersect at the point negative 2, 0. As far as a check, I've just used that first equation to find the x value, so I can go back to the second equation and do a check. My second equation was negative 2x plus 7y equals 4. I'm going to check the point negative 2, 0, and make sure that is a solution to this equation as well. So I have negative 2 times, and in for x, I also happen to have a negative 2 in this case, plus 7 times, and in for y I have 0, equals 4. Negative 2 times negative 2 is positive 4, plus 0 equals 4. So it does check. So I feel good about this being the solution to the system of equations.